All right. Hello, everyone. Thanks for coming to this recitation. Today, we're going to speak about representations, representation learning, and autoencoders. And the recitation will be conducted by me and Shentong. So first, let's talk about the importance of representations. So the choice of representations when you're trying to solve any given problem is key to solving that problem correctly and efficiently. And a few examples to motivate this include the first one, which is long division. So for example, if I ask anyone to divide 210 by 6, this is quite a straightforward task for most of us. But if I ask you to do the same thing in Roman numerals, then that becomes a little more challenging. And in fact, most people will probably try to convert Roman numerals to the Arabic numerals first, and then go about dividing 210 by 6. And that's because when we represent the number 210 in Arabic numerals, it becomes much easier to solve this problem than to do it in Roman numerals. A second example is that of binary classification using a linear classifier. So the same data set can be represented in different ways depending on how you choose to represent the features of the data set. So if you use Cartesian coordinates as shown in the graph on the left, it becomes impossible to do binary classification with a linear classifier. But if we represent the same data set using polar coordinates, then this task becomes much simpler. And a final problem, which is generally applicable in computer science, is say if you have a problem of inserting a number into a sorted list, then if you represent this sorted list as a linked list, your computational complexity is going to be of the order of big O of n. But if you used a balanced tree, such as a red-black tree, to represent the sorted list instead, then the complexity drops and becomes order of log n instead. And so the point that we're trying to drive across here is that for whatever task you're trying to solve, the representation of the data and the problem that you come up with is key to solving that task correctly and efficiently. And this notion of using the correct representations transfers to machine learning problems as well. And in fact, most machine learning problems today rely heavily on the process of feature engineering, in which a machine learning engineer or a data engineer spends a majority of their time coming up with better features from raw data. And they generally rely on a large amount of domain knowledge to come up with these features. So it would be really interesting and really useful if instead of doing this feature extraction and feature engineering by hand, we could instead do something like representation learning, in which we're learning representations of the data that make it easier to extract useful information when building classifiers or other predictors. And this is a quote from the paper listed on the slide, at the bottom of the slide. And this paper says that representation learning has become so important in the last few years that it's become a field in itself, and so much so that there's even a conference dedicated completely to this called ICLR. And so in recent years, we're seeing a shift from handcrafting these complex features from the data to being able to learn these features automatically and in an unsupervised way, and usually with a neural network, or at least in the context of this class, with a neural network. So these learned representations often have some desired properties that we want them to satisfy. And the one that we care about most is that these learned representations should be useful for some downstream tasks and should be able to be used for a variety of tasks through transfer learning. And certain other things such as interpretability or fairness or other notions which are becoming more and more popular in research. But I recommend that you read the paper to go through a list of all the properties that one might want their representations to satisfy. So what is a representation? As it turns out, we've seen several instances of representations in this course already. If you recall the network that you built for homework 1, part 2, when you were doing phoneme classification, what you did was you took a chunk of the MEL spectrogram from the speech utterance, flattened it and passed it through a multi-layer perceptron, and ended up with something called an embedding, which was something like 256 dimensional or 512 dimensional vector. And then you passed that through a final softmax layer and got your class prediction for what the phoneme was. So when we say a representation, we mean this embedding that you end up with, which is basically a different representation of this MEL spectrogram, which you have arrived at after doing several layers and a sequence of transformations and nonlinearities through the multi-layer perceptron. We also saw this in homework 2, part 2, where the task was face classification, where you were given an original image, which was a 3D array with RGB channels, passed it through a convolutional neural network, which was a feature extractor, and ended up with a face embedding. You then passed this face embedding through a fully connected layer and ended up with, again, an ID of the face, which is a classification objective. And so in this case, your feature extractor, instead of an MLP, was a convolutional neural network that helped you learn a better representation of this face. And what you may already be seeing is that the domain that you're working with or the problem that you have at hand dictates what sort of architecture you're going to use to learn these representations. Finally, we also spoke about representations in the attention recitation a couple of weeks ago, where we spoke about encoding a sequence of inputs, which could be a string of words, for example, going from x0 to xn, and coming up with one single vector representation, which encodes this entire sequence. And more often than not, that ends up being the hidden state that's spit out by the last RNN cell or LSTM cell. And that can be passed for various tasks, such as classification into a decoder or into an attention mechanism, or so on and so forth. So let's speak about some other applications of representation learning, apart from the ones that we've seen before. The one that's perhaps the most popular or most famous in NLP is called word-to-vec, and many of you might have come across this already. I've cited the paper at the bottom of the slide, and those of you who aren't familiar with this are recommended to go ahead and read this paper, because you'll probably see this time and again in a lot of NLP literature. And in this paper, the authors proposed a method to basically learn representations for a dictionary of words. And these representations make several downstream tasks easier, such as sentiment classification, question answering, and so on and so forth. You can also do this in the speech domain, but instead of using MEL spectrograms as we've been doing in this course, you can directly look at the waveform of speech, the raw waveform, and come up with some representation that makes downstream tasks such as word classification or letter classification much easier. And so there's been a trend of a plethora of work following this sort of representation learning literature, where the trend is that the new method, the new proposed method, improves performance on the given task, and typically also demonstrates usefulness of this learned representation on many other tasks than whatever the baseline did. For example, in text, you started with word-to-vec, but then people started developing better and better representations through models such as Elmo or GPT-2, GPT-3, or even BERT. So the BERT paper was so groundbreaking because it showed that it was not only useful for a single task, but it in fact established state-of-the-art on 9 NLP tasks, if I remember correctly. An analog in the speech domain is Mockingjay, which is a BERT-like model for speech. And it shows that the representations that you learn through Mockingjay are good not only for word error rate or letter error rate, but also for phoneme error rate, does much better than state-of-the-art on reducing phoneme error rate, and also on doing sentiment classification directly from raw speech utterance. So the trend in learning representations for many problems is that you have a lot of papers coming out which are anything to vec, where you can convert any sort of problem and embed it in latent space and come up with a vector to represent that. For example, there's speech to vec. There's something called node to vec, which takes an entire graph and comes up with a vector representing that entire graph. So this could be very useful for network problems or graph-based problems. And you can apply this method to any sort of problem. In fact, someone's even come up with a way of developing representations for Major League Baseball players, and they call their method batter or pitcher to vec, which might be interesting for you to read up on. A few recent trends that are coming up in representation learning are that of interpretability. So when you come up with some representation for the given input, say a vector for a word or a vector representing an entire image, it's not always clear what each of those dimensions in the latent space correspond to. Just because you've passed that data through so many nonlinear transformations, you don't know what the neural network did with the data to assign some sort of meaning to each of those latent dimensions. And so you can come up with clever tricks to apply some constraints in your objective function on the latent space to start to develop some sort of intuition or meaning for what each of those latent dimensions mean. And what we see in the image here is an application of a class of generative models for images where you feed in an input image and the model spits out another image. And these models have been trained on a data set called the 3D chairs dataset. And what the different rows represent is that these different models, when constrained to learn some ground truth meaning for those latent dimensions, come up with meanings such as azimuth. So in the first row, you see that the chairs are overall the same, but they differ only in how much rotation there is in each of the columns. So this means that there is a dimension in your embedding that if you perturb a little bit, everything else in the output stays the same, but the rotation of the chair differs. And similarly for width and leg style. So this image is trying to show how different models are better or worse at doing these. And you can see that the first model didn't even learn to do this for width and leg style, but the beta VAE and VAE were relatively better or worse at doing that. A second trend is that of fairness. So machine learning models are increasingly being used in very important social tasks such as recidivism prediction or predicting how much health insurance premium to charge to a person. And it turns out that when you optimize for accuracy, you don't always optimize also for fairness. And even though overall it looks like your model is being very accurate, when you take the predictions of the model in account with the context of certain demographic information, such as the race of the person or their age, or how much income they have on an annual basis, it turns out that these models are not always fair. And so we really care about learning fair representations and not just representations that are good for accuracy. So if you're interested in this sort of research, I highly recommend that you read both of these papers listed here. So this brings me to the end of my portion of the recitation on representation learning. And in summary, we want to remember that representations are learned in an end-to-end manner. They are often learned in an unsupervised manner, and they are learned to be useful for some downstream task or tasks. when you're working on a problem where you're thinking about which representations to use or which pre-trained models to use, it is often important to pay attention to what pre-training objective was used to learn these representations, and consider model architectures used and suitability for your task. And a quote from the deep learning book that I would like to end on is that, generally speaking, a good representations is one that makes a subsequent learning task easier. The choice of representation will usually depend on the choice of the subsequent learning task. Right. So that's the end of this part of the recitation, and I'll wait for a couple of minutes if you have any questions. Otherwise, Shentong, you can start your portion on autoencoders.
Hi, Anurag. I have a question regarding the last slide. So what do you mean by representations are learned end-to-end? Does it mean that it's learned together with the downstream tasks?
Yes, exactly. So end-to-end, meaning that you don't have separate parts of your pipeline where you're just doing feature extraction separately and then putting those features into a deep learning model. What you do instead is typically you just start with some raw data, feed it into the neural network, and expect that the neural network will learn the representations and transformations.
I see, got it. And then that particular neural network is learned together with the downstream tasks.
Yes. Typically, you have one task that you learn the representations for. And when you move to a transfer learning sort of setting, you can choose whether or not you want to keep those representations frozen or you want to keep modifying them through backprop. So you can freeze the weights and keep those representations learned from the primary task as they were. Or when you start fine-tuning them for the downstream tasks, you can choose to unfreeze them and optimize them again for the downstream task as well.
Got it, thank you.
No problem. All right, so the rest of the questions can probably wait until the end of the recitation then, and Shentong, you can start with your part.
Yeah, okay. Let me share my screen. Can you see my screen?
Yes.
Okay. Yeah, hi guys. Let me talk about the autoencoders. So the autoencoder is usually be used to encode some modalities in a shared space, and we often train and we also use the representation in the encoder, and we will train the downstream task, and in the downstream task we will keep only the encoder part, and so the advantage of this this way of training is to use some robust architecture, and also the encoder can reconstruct some missing modalities if it is trained well. But it also has some disadvantages or some drawbacks. So maybe we will need some separate training, and we also often cannot achieve some comparable performance compared to some pooled or coordinated representations. So the autoencoders are very popular in the 2019 or not 2019 but 2017 or 2018. But now we were using some cross modality autoencoders. For example, we can input some audio input or some video input X, and we can input the audio and the video into the encoder. and we can learn some representation by this encoder, and we also can learn the encoder edge, not encoder edge, but the representation edge by two separate encoders for the audio or the video. In the shared space, we have the edge, and then we have the decoder part for each representation, or we can sample the edge or the same edge from this space, and then we can use two separate decoders to reconstruct the audio or the video. So this is a basic architecture of autoencoder for cross modality, and often autoencoders can be trained to reconstruct the input. However, simply reconstructing the input is useless because, for example, we have the original image or the audio. We want to generate some new things, right? So we don't want to generate the same thing as the input. So actually, the output of the decoder is not what is needed. So maybe in the lecture, the professor will talk about the variation autoencoders. So the variation autoencoders, we can generate some new things. We will not use the decoder part, but we will use the edge. Not use the decoder, but we will use the edge to, use edge to generate some new things. So there are several types of autoencoders, and the first one is the undercompleted autoencoder. So in this type of autoencoder, we often have some smaller code dimension in the shared space than the input dimension. So the dimension of H here will be smaller than the dimension of X. So we will minimize loss function in the form of here L represent for the the loss. So we will minimize this objective, and L here means the mean squared error loss. So for example, if we want to reconstruct an image, or we want to reconstruct an audio, we can minimize this mean squared error loss between the original image and the output from the decoder. Actually, usually, this complete autoencoder can reconstruct the input, but it cannot learn some meaningful features in the shared space because so actually so the over complete autoencoder, if we want to increase the dimension of H in the space, we may not learn something useful from the input. So we may want to decrease the dimension of H in the space. And also we have another type of autoencoders. So it's called sparse autoencoders. So actually in this type autoencoder, we want to force the autoencoders to learn the hidden representation edge to have some zeros, or we want it has many zeros as possible. So we add a constraint in the original objective function. So here the L is usually something like a mean square loss, or if you guys are familiar with the GANs, so we will also can use some perceptual loss to reconstruct the image. So this this is a regularization penalty enforce the sparsity of the hidden representation. For example, we can add a one norm here to to restrain the, to restrain the hidden edge to be sparse. So yeah, so if we have a large, we have a large dimension of edge, and we can also use learn some meaningful features because we have some entries in the edge to be 0. So yeah, so it doesn't matter if it is over complete or undercomplete. So this regularization penalty is used for. Okay, the third type of the autoencoders is used for deloizing. The deloizing autoencoders can operate on some corrupted versions of the input. For example, if the X is a corrupted image, we can deloize the image for to reconstruct or to deloize this image. So the loss is the same as the loss before, like mean square loss or perceptor loss. But here tilde x, the tilde x is x plus noise. So here noise, the x plus noise is the corrupted version of an input or an image. So the model or the encoder or the autoencoder must learn how to remove the noise from the input. So actually, in this process, the noise removal, it can end up learning some useful features in the space, in the shared space. So we can learn some useful representation in the space.
Shenrong, there's a question for you which asks, why do we want as many zeros in H? It's a kind of weight decay question mark. I think this was to do with sparse encoders.
Yeah. Actually, it's kind of weight decay, but it's a kind of like a regularization method. We don't want to the edge, which is very dependent on this data set. So we want it generalized well to other domain data sets. So if we didn't add this regularization, and the edge will is very dependent on this data set, it's not very good, right? We want it to generalize, and we want to learn some meaningful features. Instead it will learn some like it will learn some features that are very dependent on this data. It's not very good. So we will add some sparse regularization on this edge. Yeah, it's kind of weight decay, but yeah, weight decay also. The weight decay is also a method for regularization, right? So yeah, you can regard it as a weight decay, but it's also different. Yeah, I guess there are there are 3 types of autoencoders, and also the last type of the autoencoder is called a contractive autoencoder. So actually the representation is also learned in the autoencoder in the space, right? So the contractive autoencoders, also we can use some contrastive loss, or we can compare the I don't know if you guys are familiar with some popular representation learning in this in this 2 years. Sounds like we will use 2 autoencoders, and not 2 autoencoders, but we will use the same autoencoder, the same encoder, and in the encoder in the edge part, we will define some contrastive loss in the edge, and we will learn some meaningful representation in the edge space. So we can input some image or audio. Yeah. So let me see the chat. Yeah, I mean, yeah, the why we use a sparse regularization? Yeah, we can force some weights to be 0, and yeah. So if we didn't add this regularization, I think the weight or the model is very dependent on this data, right? So it will not. It's not very desirable for us to learn some robust or some general reliable representation. So yeah, I guess they're all my part for the autoencoders. And if you guys have any question about autoencoder or some representation learning, or some, if you are familiar with, I don't know if you guys are interested in BERT or transformer. I think they're also a good way to pre-train some good representation that are used for downstream tasks, right? So yeah, but all the encoders are some basic architecture to learn some useful or meaningful features. Yeah. So yeah, that's all my for my part. And if you guys have any question, please feel free to ask.
Okay, so if there are no questions, then we will stop the recording.